Hi, I'm Randall Heyman, a university academic. This is it's one of my Corona Help playlists where I make quick turnaround videos to help students and educators during the coronavirus outbreak. So if you'd like me to make a video for you, just contact me and I'll help if I can. Okay, so in this video, this comes from some comments that I've been making with Colin under some of my videos. And it follows on from a video I previously did about modular arithmetic. And what we said was where you have something like AX is equivalent to B mod D, well, there's a number of possibilities. You can have no solution. For example, 6x is equivalent to 1 mod 8. You can have one solution. For example, 6x, actually, let's make it this. 5x, it doesn't have to be 1 here. I suppose we could go 5x equals 3 mod 8. And multiple, so more than one solution. So here I'm thinking of something like 60x is equivalent to, well, actually, let's do it in terms of everything in terms of mod 8 here. I suppose if we go 6x is equivalent to 2 modulo 8. And the defining thing here is that the GCD of 6 and 8 is equal to 1, but the GCD of 6, 8, and 1, so the three numbers concerned, does not equal, 6, 8, and 1. Yeah, that one is equal to 1 as well. Here, sorry, no solution, sorry. So that one should say not equal to 1. Yeah, this one here, I suppose the defining thing is that the GCD of 5 and 8 is equal to 1, but the GCD of, that's probably sufficient actually. Not sure about that one. And then this one, we have that the GCD of the 3, 6, 2, 8 is not equal to 1. Okay, so we've sort of got a fairly good handle on that. And then Colin was talking to me a bit about this idea. What about if we look at this? So very specific, actually let's make that D. So we can make this a bit more specific if we choose to. There's no need to, but you could look at that, for example. Now here, the GCD of this one, and this one, this one. Well, yeah, you can either get no solutions or multiple solutions, but you can't get a single solution in that case. Anyway, where would we go with this? Where could we go with this if we are looking at playing around with it and maybe coming up with some interesting results that might be publishable? So the first thing we could do is look at the GCD case. So you might say let D, D is probably not the best thing to use there. So let's not use D. I'm just creating a function here. So you might go let V. V is a function that has two inputs, A and B, and it's going to be the number of solutions to AX is equivalent to the GCD of AB modulo B. And what we might be interested in is then looking at this thing. This is what would be maybe interesting. So we're going to sum up all these VABs. So we're interested in summing up all these number of solutions. And here, this is for A and B are between all of the possibilities of A and B being between 1 and M. And we'd call that maybe, we'd call that SM. So the sum over all the M's here of the number of solutions to this. Now, the variations you could look at here is you might do something like A, B, so the product of A and B is less than M, or you might do a double sum, which where basically A can go up to M and then B can go up to A. This is sort of a triangular summation. This is a sort of hyperbolic summation. This is sort of a rectangular summation. But what you would be looking for here is some understanding of how SM grows. Like ideally, you'd like an exact formula. You know, you might get, I don't know, you might get, it could be M squared divided by the Riemann zeta function evaluated at 2, and then you take the floor and minus something ... So you could get an exact formula, but more likely you would get a asymptotic formula. So here you get something like you'd be looking at something that might be like I said, so maybe zeta 2 times M squared. Plus then there'd be a big O term, which would be an error term. And here you'd like to get the error term as low as possible. You'd certainly want to get it lower than M squared. So you might want it to make it, it might end up being M times log M as the error term, the best error term that you could get. So that would be an interesting thing to have a look at. Now, more likely what Colin is interested in is not having that GCD requirement. So we could do the same thing in a more general way. So let U of A, D, M now be the number of solutions to AX is equivalent to D modulo M. And then we would say let Tm, I suppose this would have to be T something else, wouldn't it? Let's call it Ty, which is equal to the sum 1 is less than A, is less than D. Well, it depends what you want to do here, actually. Yeah, you could do this. You could make this, so you set an M, and then you try and solve this. U, A, D, M. Could do something like that. Once again, you'd be looking for an asymptotic formula. There's, looked in regard to all of this, there's a fair bit that's known about what the number of, say, A and M, what's the, if you like, the probability that A and M are co-prime, or what's the probability that the GCD for A and M is equal to 1. A lot of is known about that. This is actually turns out to be, well, probability is not well defined in what we talk about, but loosely we would say 1 on zeta 2. And similarly for pairs, what's the probability of A, D, M are not co-prime? Oh, sorry, so the probability, I've done some work on these sort of areas of mathematics. So the GCD of ADM is equal to 1, but the GCD of, I don't know, AM, sorry, that's not equal to 1, but the GCD is equal to 1. Those sort of things are quantifiable. And so you could use them to start to build an understanding of how you get to something like this, or this one that we had up here. And I just mentioned one third thing before I go, and that is that there may be some merit with some of these in looking at it graphically, which is an interesting concept in itself. Let's draw this. So let's call this little x. And let's just use modulo, let's consider modulo 80, because that's what Colin was focused on a little bit. What we could do here, if we're dealing modulo 80, of course, you can't get anything beyond 80. So what I could do is I could draw a line here at 80. And I could draw a line here at 80. I'll label it in a sec. Whoops. Okay, so this is 80 and this is 80. So we want, say we want AX to equal B modulo 80. If you think about what AX is, I could draw AX. X is 0, so AX will be 0. And then if I head off from here, I can actually plot it like a normal graph that we would have done at school. Let's say I make it 2x just for the sake. If I make it 2x, it's going to go up to here. Well, that wasn't halfway, so let's not make it 2x. But at this point, what happens is that this thing goes down to here. So I would sort of go down here, and then I would start again, all at the same angle. Once I hit this point, I would then go across to here. And then go up here. Whoops. You get the, anyway, hopefully you get the idea. Now, in the case where the GCD, where you can see that if I made A equal 40, it would just go from here. Sorry about that. We go up here, the line would go up to here, to here, to here, to here, and then it would start again. So it would loop very quickly. So if the GCD of A and 80 is not equal to 1, well then you'll only get a few lines, whatever that means. If the GCD is equal to 1, well then you'll sort of get every line at a given slope, because the A determines the slope. So now, of course, this A here, this line here, this angle theta is determined by A, and so there's only a number of possibilities. So sometimes looking at graphically can give you a little bit of insight as well. Anyway, that's just sort of a random riff through some ideas that follow on from what Colin was talking about. If you've got any comments, let me know. Otherwise, I'm just going to end it here.